There are ways to know which side of the equation will be more favored during or after reaction. We call that thermodynamics. Okay, so thermodynamics, these are just changes in the equilibrium with respect to temperature. So thermodynamics will help us to understand which side of the reaction equation is favored. Is it the reverse, the forward? Is it the left, the right? So let's say you have this generic reaction, okay, with the balanced coefficients. You know the way you write an equation of reaction where A and B reacts to give you C and D, and then now you have to balance it to get the coefficients, the leading coefficients, lowercase a, b, c, d. So let's say we have this. And then we have an equilibrium arrow or arrows shown there. So the equilibrium can be defined by this equation here. So where KEQ is the equilibrium constant. So usually you take the multiplication of the concentration of your products and take their powers to be their balancing leading coefficients. So in other words, you have the product of the products, like the multiplication of the concentration of the products, divide by the multiplication of the concentration of the reactants. Okay, again, do not forget to use your leading coefficients, the lowercase a and b up here. Okay, so that will define KQ. So if KEQ equals to 1, neither of the side is favored. The reaction will equally go forward as much as it goes backward. Now, if KEQ is less than 1, then the back side is favored. Okay, if KEQ calculation gives you a value that is that's greater than 1, then that means that the forward side of the reaction is favored. Now we also use energetic plots, energy diagrams or graphs to explain the same concept. Oh, this is just saying what I just said. KQ tells us the direction of the equation that's favored. If it's greater than 1, the products are favored, so the reaction goes from left to right. Larger KQ is the larger the KQ, the farther it is to the right where the products are. So if KQ is great, then the reaction goes forward, and that's what probably you want. Okay, so now consider this reaction. So you have A reacting with B, and it could react going forward or backward probably. We don't know yet. So we are using organic molecules here, and this reaction is called esterification because we are making an ester, esterification, so to speak, but you really don't want to force yourself to know that for now. So let's say you want the reaction to move forward. There are several things you can do. You can add an acid catalyst, or as you form your product, you can take it out because now you're creating space on the right and more products will form. So another thing you can do is to add more reactant. So for example, if you add ethanol, then the reaction will move forward because you have more of the molecules to react with the other one. Okay, with the acetic acid. In this case, this is acetic acid. So increasing the amount of ethanol will cause the reaction to go forward. Removing your product as it's formed will cause the reaction to go forward. Removing the water as it's formed, it will cause the reaction to go forward. So any of the product can be taken out to cause the reaction to go forward. The easiest product to be taken out during this reaction is usually the removal of water, because you can use a drying agent in your setup to suck up all moistures from your reaction, and then now you have space, so to speak, on your right, and more product can be formed, more water can be formed, and you will be favoring the right side. in which case the KQ will be greater than 1. So removing the product or adding a reactant will favor and drive the reaction forward. KQ will be greater than 1. Okay, like I said, there are graphs that we can use to determine which side is going to be favored. There are two types of reactions in terms of thermodynamics involving heat. So where heat is released, for example, when you're cooking with natural gas in your kitchen, you produce heat. That reaction is said to be exothermic. Okay? So the change in heat is going to be less than 0 because you are dropping the energetics, the energy level is going to drop to get your product. So usually change in H will be negative for exothermic, and then change in H for endothermic will be positive, in other words greater than 0. But I'm going to explain this shortly. So just remember that in exothermic reactions, heat is released. Heat is released from the system, whatever is being reacted. And then in endo means into. In endothermic reaction, heat is added into the system, into the reactant. Heat added. So any bond breaking process must be endothermic because you need some energy to break the bond. Just like you want to break the pen, you need to add energy into the pen as it breaks. So the reason why delta H is greater than 0 in endothermic process because you are adding some energy into the system, like whenever you want to break a pen. Bond forming processes are usually exothermic. Heat is going to be released. Bond breaking is endothermic. Let's look at this diagram. Now, can you tell which of these two is going to be endothermic, which one will be exothermic? It's very simple to tell. These guys right here are your reactants. Okay, those are your reactants. Okay, they are high in energy on y-axis. This is your product. Okay, so probably this is an addition reaction where you took ethene and then you added HBr, just like we did in addition reactions, to get ethyl bromide or bromoethane, which is just that. So you see the products are down here on the y-axis. The enthalpy of H is low. So the difference between these two is going to be negative because there was a drop in energy. So change in H is negative. Therefore, this graph represents exothermic reaction. Why? Because the reactants are high in energy than products. And in this case, the KQ is likely to be greater than 1 because we usually say that the reaction is spontaneous and it's likely to go forward. Like you don't need to add energy here. Energy is released. That's why change in H is negative. Enthalpy change is negative. Heat energy is released. Now here you are moving from a molecule which is ethane. So you are breaking apart. So this is what's happening in this graph. So you have CH3, you have CH3. In other words, you have 2 electrons. So one electron goes there, the other electron goes there. So what you end up with is radical. 2 radicals. So it's a bond breaking process. Remember I told you bond breaking is endothermic. You're going to need energy to break your pen or to break a bond. So if it's endothermic, heat is added in the system. You expect the products to have high energy because heat is added into the system. The reactants will be down here. So there's a positive change in heat energy because you added heat into the system. So this graph is a representation of an endothermic process. And the example is given of where ethane is broken down to the methyl radicals. Okay, methyl radicals does not easily happen. That's why it's non-spontaneous, and the left side is always gonna be favored. Like this side, this molecule want to stay as ethane rather than just spontaneously, randomly breaking apart to form the radicals. You have to provide some energy here. And remember, we used UV light for the radical process. So because you're providing energy, the reaction is not spontaneous. The forward reaction is not likely to go unless you give it some support, unless you give it some boost, unless you give it some energizer. So the reaction of endothermic processes most likely is going to have a KQ less than 1 because some heat has to be added for it to happen before it happens. But for exothermic reactions is almost spontaneous. So you're always most likely going to go to the product side. So you see, you can use the graphs also to determine whether the reaction is going to favor the right side of the equation or the left side of the equation based on whether it's exothermic or endothermic. Okay. Now, apart from the equilibrium constant and enthalpy, okay, we need to determine what we call the transition state, which is just halfway your products, halfway between the reactants and product. Okay, so this equilibrium constant and enthalpy will tell us the direction the reaction will proceed, and will tell us if the reaction is spontaneous, which means can happen instantaneously or not. But the equilibrium constant Kq and the enthalpy H, or change in enthalpy, does not tell us how fast the reaction will go. So for that, we need a transition state. The transition state goes hand in hand with what we call the activation energy. So the higher the activation energy, the longer it takes to make the transition state molecule, the longer the reaction will take. And that's how we tell how fast the reaction will go. So in a generic reaction, where say you have reactants here, instead of drawing straight lines like we did here, let's draw mountains. So that has to be overcome for an exothermic reaction. So if the products are lower than the reactants, or the reactants are higher than the products, this system is exothermic reaction, where this is, of course, energy, or you would say change in H. So the transition state will be here. That's going to be the molecule that has bonds trying to form, bonds trying to break. So you really have to get up the mountain before you roll down, So the energy required to get to your transition state is called the activation energy. The higher the activation energy, the slower the reaction will go. And that's why the transition state theory is important and is effective in telling us or letting us know how fast the reaction will proceed. So this theory states that the reactants will proceed through a high energy. You see, like what I'm talking about here is activation energy, transition state, and then proceed to the product. So the sooner you get to the transition state molecule, the sooner you're going to get to your products. Okay? So this is the activation energy right there. That's the energy barrier that prevents you from getting to where now you want, for example, to join these two reactants. If you're reacting A and B, the two have to come close by together, and probably they'll want to make a bond. I'm using the word want because the bond is not made yet. So if they want to make a bond, then you're halfway to your product, where in this case the bond is already formed. So you are in transit, and so we call it a transition state. Okay? So the sooner you make your transition state halfway between the products, halfway between the reactants and products, the quicker the reaction will go. So at the transition state, molecules are colliding and bonds are being broken and bonds are being formed. So bonds want to be broken. I'm using the word want to be broken, and bonds want to be formed. They are not formed yet. They are not broken yet. They are almost breaking. They are almost forming. So you're in transit. It's just like you're going somewhere. You're from point A to point B, from your reactants to your products, and then halfway your journey, you are in transition state. Okay, you are not yet. You are halfway from where you left, and you're halfway from where you're going, halfway to where you're going. So you're in transit. So that's what the transition state is. So the sooner you get to 50% your journey, the sooner you're gonna get to your product in theory, to your destination in theory. So this one, the reactants are shown to be up here, the products are shown to be down here. Okay, so can you tell whether it's exothermic or endothermic? It has to be exothermic because reactants are above the product. Someone must have lost some energy. Delta H here will gonna be negative. So for this one, reactants are below the products. So in this case, delta H is gonna be positive. So this has to be endothermic. Now, which of these two is likely to happen instantaneously? The answer is gonna be this one, right? Look at the activation energy, the energy barrier, the energy required, okay, to get to the transition state is less. There's less distance from this point to this point, from this point to that point. There's less distance there compared to here. Here you really need a lot of energy to get up this higher mountain before you get your products. So that's why endothermic reactions are usually non-spontaneous. They don't easily happen unless you boost them with some energy in form of light or heat or magnetic or nuclear. But exothermic reaction, most of them are spontaneous, which means they easily happen. Okay, they instantaneously happen, probably with little help or no help at all. Okay, so the sooner you get to your transition state, the sooner you're gonna get to your product. So in this case, I will expect that this reaction will be faster than this reaction because this one has less energy barrier to get your transition state compared to this. Okay, so these two diagrams are called reaction coordinate diagrams, which shows the reactant, the transition state, and the product. Okay, so I've been talking too much about transition states. So we usually, instead of talking about the activation energy in the molecular state, we usually talk about delta G with a slash line. So delta G with the slash line. This is just an activation. This is just the activation energy of a spontaneous reaction. Obviously, this reaction here is spontaneous because it's exothermic. So now it's okay for us to use delta G slash instead of using EA because now we are specific. We are getting specific with the molecules. So, okay, so in contrast to the intermediate, the transition state has no real lifetime. Like, it does not exist. You cannot isolate it as a product and store it in a flask. You can't isolate it. You can just tell that it's there based on how much reactant has disappeared. Okay, at this moment, probably you'll not have made much of your product, but much of your reactant is in here in the transition state. So you can tell its existence. You can tell of its existence, but it's hard to time it. You can only study it by software, and that's advanced chemistry. Okay, so the TS will always have a low lifetimes. Okay, so now let me see what we have here. So you have two reactants. Let's call this A and B. So A is reacting with B. So we are pretending that this atom of A is attacking the carbon in B. So what you're really showing is that a bond is trying to be formed between the red ball and the gray bond. So this bond right here is bond trying to form. So let's call it bond forming because it's not formed yet. We are in the transition state. Let's call that bond forming. Now, because this is a bond and you have another bond on the other side, which used to be this, the carbon in the middle, it looks like has 5 bonds. That's illegal. Carbon must have a maximum of 4 bonds, either 4 single bonds or a double bond and 2 single bonds, or two double bonds across the carbon. Here in this case, we are looking at this situation right here. So if this is attacking the carbon, this bond has to break and leave. So this bond right here must break. So this one is bond breaking. It wants to break, or it's in the process of breaking. It's not broken yet. So once this is broken and once this is formed, you're going to make your product with the bond there, and then this becomes the leaving group. Okay, that becomes the leaving group. So this molecule up here that has a bond trying to form, bond trying to break, and then the rest of the molecule on the plane, this is on the plane, is called a transition state. And it can be explained by computational method, which is way above your scope. So the best example that we can use here is where OH uses its oxygen to attack this carbon, and then the Br wants to leave. This reaction is called SN2. By molecular nucleophilic substitution reaction, we'll talk about this in another chapter. So you see the oxygen wants to make a bond with the carbon. So this is your TS, and then the carbon bromine bond wants to break. This bond wants to break, but once the bromine breaks off, that's how you make your Br minus. And then of course, once the oxygen carbon bond forms, that's how you make your alcohol. All right. So this kind of helps to explain how we make our product. So the sooner you make your TS from the reactant, the sooner you make your product. So the transition state theory is very important in explaining the rate of reaction. Okay, so we can explain the reaction of propene with a proton based on a reaction diagram, coordinate diagram. The reason the primary carbocation is less stable than secondary is because it has a higher TS energy, and so it's harder to form. So what this mess here is trying to say is this. Assume you have propene, okay? Assume you have propene. And I hope you remember Markovnikov rule. So if you're reacting propene, for example, with a HBr, remember we said the dipole moments point towards bromine. This hydrogen then will have to be partially positive because the electrons making the bond reside close to the bromine than the hydrogen. So the bromine will be partially negative. So in Markovnikov rule, it states that in reactions where you are doing addition across the double bond, the electropositive element of the reagent is going to be added on the sp2 carbon of the double bond that has more hydrogen, so which is this carbon right here. So use your pi bond to grab the hydrogen. This leaves. Okay, so when that happens, this hydrogen right here is going to be added here where the CH2 is rather than here where you have the CH, according to Markovnikov addition. Okay, so you're going to get a CH3. You're going to get a CH3 once this circled hydrogen goes to the CH2 side, and then on the other carbon that did not accept the hydrogen, there's going to be one bond less, so we put a plus sign. This hydrogen right here is the one that was still there. The CH2 is now CH3 because it grabs the hydrogen from the reagent. So this is a secondary carbocation. Now assume you go anti-Markovnikov addition where this hydrogen is added on the wrong side. So this is what will happen. So if you have propene with a CH2 there, and then for whichever reason you forget the rules and you go anti-Markovnikov addition. So where the hydrogen of HBr is added where there is less hydrogens. So let's add this on the other side, and that's going to be anti-Markovnikov addition. That will mean that now the CH2 stays as a CH2, and then the hydrogen that was single there now accepted an extra hydrogen, and then because this CH2 did not accept the hydrogen and is one bond less, after the anti-Markovnikov addition, the CH2 is going to be positively charged. Now this is a primary carbocation because the C plus is bonded to one other carbon. So this is primary. This is secondary carbocation because the C plus is bonded to two carbons, that carbon and this carbon. So again, that's the primary and this is a secondary. This structure is this one and this structure is that one. So you see the primary is shown to have a very high activation energy following this arrow right here. Okay, that is the activation energy of the primary carbocation formation, and this is the activation energy of the secondary carbocation formation. So there's less energy barrier to form the transition state of the secondary compared to the transition state of the primary carbocation. So that's why secondary carbocations are more stable than primary, and for your review, tertiary is more stable than secondary carbocation, secondary carbocation is more stable than primary, and primary is more stable than methyl carbocation. So again, we are talking about reaction thermodynamics, why one is favored over the other, all because of the amount of energy barrier or activation energy needed. The lower the activation energy, the more spontaneous or the more likely the reaction will go that way. Let's see, what do we have here? The reaction of HBr with ethene can be explained in a similar fashion. So this is ethene. Now this time you have an alkene that's symmetrical, so you can add the hydrogen on either side, and if you add it, for example, on the CH2 to the left, then one CH2 which is on the, if you add it to the CH2 to the left, yes, then the left CH2 will be CH3. Okay, so we are doing addition here. There's no need to state it as Markovnikov because both CH2s have the same number of hydrogens. So if I add this hydrogen to the CH2 on the left, the other CH2 will be one bond less. It's gonna get a positive charge. Okay, so you see, again, this is a primary carbocation. Is it stable? Not. So the TS is very high as we are in the process of making HBr, but not yet formed the new CH bond. The intermediate carbocation is lower in energy as the new CH bond has formed. So what you're looking at here is this molecule here. Of course, it's a primary carbocation. There's no other choice of making a secondary, so that's the only one we're looking at. Carbocations are usually called intermediates because they are true molecules that can have a longer lifetime compared to the transition states. So what the transition state is showing here is that the hydrogen, okay, in this case they used the right CH2 to accept the hydrogen. So if you have HBr, so the what's drawn on the chart is the opposite of what I did. So they used the right CH2 to accept the hydrogen, and then Br falls off. So that's what we're doing here. The hydrogen is here. Once it wants to be accepted by the carbon on the right, and then the other CH2 stays as a positive sign. So now you have a CH3 because once you do this addition, you're gonna have CH2 with a positive on the left, and then the one on the right will be a CH3 if this hydrogen is added to the CH2 on the right. So this structure right here is what's shown on here. Okay, that arrow is just pointing that this molecule is that molecule. So because it's a carbocation, and of course it's primary, it's gonna be called an intermediate. So once you form your carbocation, now the Br that fell off will come to try and make a bond with the C+. So it's trying to make a bond. So this is a bond wanting to be formed, just like this one was a bond wanting to be formed. Okay, so once the bond is formed, then you get your product where the Br is now attached to where the C+ was, and the product will be of this nature. Let me draw it big so you can see it. So when the reaction is done, you will have added a hydrogen and a Br across the double bond. So you have two transition states. One, formation of carbocation. The second transition state, the nucleophile attacks the carbocation to get your product. So you have an activation energy here, E2, and you have activation energy here, E1. So which of these do you think is the rate determining step? The rate determining step is going to be formation of your intermediate, because to form your intermediate carbocation, there's a higher activation energy. So the sooner you form your carbocation, the sooner the reaction will go, because the second transition state does not require a lot of energy to happen. EA2, activation energy 2 is less than activation energy 1. Okay. All right, sure. You can also use a catalyst. Catalyst can be used to lower the activation energy. So let's say you have glucose being oxidized to give you CO2 and water. In the presence of an enzyme, which is a catalyst, The reaction will go faster because the activation energy is reduced. Instead of going way up, it's going to take the blue pathway. Okay, the temperature can affect how quick the reaction will go. Usually what temperature does, it just increases the energy state of the reactants, and that way, in turn, you will have reduced the activation energy, and then the reaction will go faster. In fact, whenever you are heating molecules, they randomly collide with each other, and that's how they quickly react with each other. The reason is those molecules gain energy. So if these are the reactants right now, when cold, by heating, the reactants will be right here. In effect, you will have reduced the activation energy, which would have been higher if without heating. To convert your products to your transition state, to convert your reactants to your transition state, then to your products, the activation energy will be reduced by increasing the temperature. So temperature does help for the reaction to go faster. Okay, that's the end of chapter 3.